Thanks so much, Sarah, and thanks for having me. So my name's Pippa, and I'm a doctoral researcher at Imperial College, not at the School of Mines. I actually sit in the Department of Civil and Environmental Engineering, but I'm actually a chemical engineer. So you can kind of you can sit in multiple different areas and be working on interesting problems. Um, so my PhD work is part of a European Union Horizon project called DETOCS, and we look at cement decarbonisation. So I study the environmental performance of one decarbonisation option for cement, which is low clinker cements. And today I'm going to talk a little bit about how they work, responsible material use in cement, the kind of carbon problem we have in concrete, and focus on how we can, I guess, problem solve using low clinker cements to support decarbonisation. Did that slide move? Great. So, concrete is a critical material. It's one of the most widely used materials in the world. You're probably looking at some right now in your field of vision, and that's because it's cheap and durable and it's essential for modern infrastructure. So, in 2020, global use of concrete reached about 14 billion tons, and that required about 4 billion tons of cement. The demand for concrete products is only expected to grow to 2050, particularly in non-OECD regions to support development and urbanization. But that's over the same time frame that we've got a carbon problem. So our appetite for cement accounts for about 7 to 8% of global anthropogenic CO2 emissions, making it a focus area, as Sarah said, for net zero. But I think there's huge potential in cement decarbonisation and not only some quick wins, but useful wins. The challenge is really clear. We have to meet these reduced emission goals and meet the increasing demand for concrete products that support development and urbanization. And because a lot of the demand is in emerging markets, it's critical to prioritize decarbonization strategies that are also cost effective. So it's not good enough to kind of slap a carbon capture unit on current production and call it a day, because that'll increase costs dramatically. So most of cement's CO2 emissions come from producing a material known as Portland clinker, which is the main component of modern cement. We call modern cements a Portland cement because of their similarity visually to the high quality Portland stone. That was so it's a bit of a branding thing. But the way we make clinker is we heat limestone with siliceous materials at high temperature. This process releases CO2 both from the chemical reaction, which is difficult to abate, and from fossil fuel combustion. So it's about 1450 degrees in the kiln. Producing 1 ton of clinker has a carbon footprint of about 850 kilograms of CO2 equivalent. So, one of the key strategies in cement decarbonisation is to lower the clinker content in cement, and it already works and we already do it. Today's cement that you'd use or buy is already blended and contains on average about 75% clinker by mass. The target for 2050 is that the average global cement needs to fall to about 52% clinker. But we want to maintain the performance and make sure that we continue making good quality, strong, durable concretes. One of the challenges in reducing the clinker content from today's levels is the availability and the reactivity of substitute materials, which has driven significant research into identifying potential materials. And that's demonstrated here on the chart on the right, which encompasses kind of all the literature into researching new material compositions that we can use in cement. That includes traditional substitute materials like blast furnace slags and fly ash, to exploring areas like mine waste, biomass ashes, and even new manufactured products like calcined clays. Having trouble changing the slide. Okay. So to understand these materials better, it is briefly useful for everyone to understand how cement works. So here's a little cement 101. Cement is a powder that reacts with water. This reaction is known as hydration, but cement is more complex than just a powder, and it contains many different reactive mineral phases. However, as hydration progresses, these reactive phases dissolve in the water and they precipitate lower density hydrate phases. These phases fill up the space that was previously occupied by water and bind everything together in the strong, solid concrete. So cement clinker contains reactive calcium silicate phases, which we've made at high temperature and they're pretty unstable, which dissolve quickly. And they precipitate the hydrates and another phase called Portlandite. Clinker substitute materials generally react more slowly and they consume Portlandite to produce hydrates, which means that they mainly contribute after the clinker has been reacted. And it also means that we can't fully displace clinker in cement. So overall, strength development comes from dissolution and precipitation reactions, with clinker dominating in the early stage and early strength development, and substitute materials contributing later. So my research kind of combines two areas and techniques. I do life cycle assessment, and I also look at modeling cements to evaluate both the environmental impact and the technical performance of cement mix designs. So with life cycle assessment, we calculate environmental impacts by quantifying the inputs and outputs of material and energy into a system. But a key challenge for, I guess, emerging materials is access to limited data. So traditional LCA is generally based on operational surveys, but we can prepare data from multiple sources, such as process modeling and other technical reports. Once we have life cycle data, we can use it to evaluate cement mix designs if we also understand their performance. But as we've just discussed, the design space for potential cement mixes and different materials is really large. So being experimentally validating all of these material combinations is impractical, time-consuming, and expensive. So we use modeling techniques to estimate the performance and first identify promising mixes before we get to that, I guess, later experimental certainty stage, where in our models, we're combining the reaction kinetics, so how much material dissolves, with thermodynamics, which predicts which phases form in cement. Then once we have the phase formation, we can use that to estimate properties like compressive strength and understand the durability properties, which allows us to compare different cements fairly based on both emissions and performance and go for a kind of apples to apples basis. So part of my work involves collecting data on how different clinker substitutes are produced. And we can then compare emissions from common processes that we use, like calcination, drying, grinding, and quarrying. Comparing data sets between materials also helps us build confidence and certainty in the result and helps us identify both lower impact production routes for producing clinker substitutes. And we can use this data to then estimate emissions for new materials which might use the same processes. However, this level of analysis doesn't yet tell us how the materials will perform in cement. So more reactive materials are likely able to displace more clinker for the same performance. To assess the reactivity of clinker substitutes, a common experimental method is called the R3 test, which uses a simplified hydration experiment to measure the amount of heat released and the bound water. Performance also depends on some physical properties like particle size and mix design. So predicting behavior of the clinker substitute materials is an ongoing research challenge. But by using R3 heat release as a proxy for reactivity and comparing reactivity and emissions from our LCA data, we can identify materials which might have good performance as composite cement mixes, like calcined clay, which have both high reactivity but also relatively high carbon footprint compared to the other substitute materials. Even so, the higher emission clinker substitutes roughly have half the emissions of clinker. So replacing the clinker with these materials will reduce the overall impact of composite cements. And just an example here is some mixed designs that we've calculated compared to a high clinker CEM1 cement down to about a 50% and lower clinker cements made with limestone calcined clay and blast furnace slag. So what we see from this is that the degree of substitution is more important than the specific material used. So higher footprint substitute materials can produce lower footprint cements if they allow more clinker to be replaced. And calcined clay is particularly promising because it's produced from widely abundant common clay deposits and at a comparable cost with conventional cement. And the performance is there as well. So limestone calcined clay with 50% clinker has been experimentally validated to have comparable mechanical performance to conventional cements. So we can meet our 50% clinker factor target with calcined clays, but what can we do to go further? And that brings us back to clinker, which it kind of gets a bad rap in the cement story because it's bringing all of the emissions, but it's super reactive, and we know the chemistry really well, so we know how it works. And clinker is like really poorly. It's got a wide definition of what can be a clinker. And it's made of these reactive calcium silicate phases. And the most reactive phase is known as alite, which is tricalcium silicate, which is highly reactive, but it also has the highest carbon footprint of all of the clinker phases due to its calcium content, which again creates a trade-off between emissions and performance. So what we did was we studied clinkers, varying the concentration of alite in our model. Compared to the less reactive but lower emission B-like clinkers. And our modeling shows that by increasing the A-like content, it increases the volume of hydration products at early ages, as well as the mortar strength, and results in more formation of Portlandite, which supports the reaction with clinker substitutes. So optimizing the clinker composition can actually enable further substitution of clinker than we see in conventional cement mixes now. And when we look at that on a unit strength basis, the best emissions per strength results come from the higher strength systems, which have the higher A-like content clinkers, which highlights, I guess, the same thing we saw with the clinker substitutes, is that higher emission materials can produce lower emission cements depending on how we use them. So we can also use this integrated modeling approach to study decarbonisation strategies at the clinker level, which include alternative fuels or alternative raw materials, which can decarbonise the clinker, but as they change the clinker chemistry, they may actually result in less reactive and therefore less substitutable clinkers. So it reinforces the need for integrated approaches to understanding cement decarbonisation strategies. So that's kind of a whirlwind tour of the world of cement decarbonisation. And I guess the key takeaways is yes, clinker substitution is a key strategy for decarbonising cement, but it's not just about selecting the lowest emission materials. We have to consider them in tandem to performance. And clinker's not the bad guy. So we need to really consider the high potential in optimizing clinker as part of the low carbon cement story. And overall, both the clinker and substitute materials have to be considered together to achieve high performance, low carbon cements that we need for, I guess, net zero. Thank you so much.
Fantastic. Thank you so much, Pippa. Everyone, round of applause for the fantastic Pippa Edwards. Now, the first question, that is one of the most important questions, is who came up with the title DETOCS? Because that is genius.
Yeah, that's one of my co-supervisors, Wilson, who works at Fuller Technologies in Copenhagen. I'm in an industrial PhD, so we work with a few different companies. But yeah, he came up with DETOCS as the kind of project name, and it does have an acronym, but it's not at the forefront of my mind. But
That's
yeah,
quite all
he's very
right.
good. He's very good at the coming up with the good names.
Yeah, no, it's a good one. It's a good one. It's a good one. So with this, in terms of your research, so I mean, it's fantastic in terms of what you're finding at the moment. What comes next? Like, how do we get some of this actually into the world so that we can see those positive changes?
Yeah, so I think in terms of what comes next in the cement world, I guess there's an acceptance of calcined clay and so-called like limestone calcined clay LC3 systems as something everyone really needs to push for. And we're seeing a lot of investment in producing calcined clay systems.
Mm,
So I would say there's a lot of momentum there for these introducing new materials. In terms of what comes next, getting something like a high A-light clinker from a paper that we published this year to a production system is obviously takes time. Um, so it's important, I think, to have like the staged rollout of different materials and people, I guess, being aware of in industry what materials are available, and a lot of it comes down to the local market factors. So a material out of the wide range of materials that are being investigated, there is not really one solution for each local context.
Hmm.
So I guess it's more of an awareness, but there's plenty of action on the industrial side in cement. My industrial background is more in the energy sector, so I was really pleased coming to cement and seeing how integrated the academic side was with industry. So I think it's really promising. It's a promising like slice of the pie to see people actually getting after the easy wins.
And so with that, so from an industry perspective, if you are a concrete company, you want people to want concrete because that's, I guess, the underpinning demand side of your business. But I guess with regards to the broader picture and the carbon footprint, the climate side of things, I remember we had a conversation with yourself and one of your supervisors, Rupert, and you shared some fascinating figures around, well, actually, if we got rid of concrete, or instead of building our buildings from concrete, we built them from wood. That that actually is a meaningful shift.
Yeah, totally. And I think it's not necessarily even just in when, or I guess my work is looking mainly at the cement mix design, and how much we can reduce emissions in that area. But you're right that there's a whole series of changes that can happen together in terms of, at the construction stage, do we need to use as much cement and concrete to build the same structures? Where can we replace other materials?
Mhm.
Um, so yeah, there's a huge, I guess, area of opportunity to introduce new materials across the whole kind of construction value chain without just focusing on, my work is very concrete, cement, clinker, alite, which is a very kind of narrow view.
Sounds like a PhD.
But yeah, there's you can go wide and you can go deep on a whole bunch of materials to support decarbonization in construction.
Yeah, no, absolutely brilliant. So I think with that, Pippa, I know there are lots more questions, and I've been messaging with people behind the scenes around concrete being degraded by the steel that's inside it, all of this kind of stuff as well. But maybe we come back to that later.
Sure.
Everyone, please put your hands together for the fantastic Pippa Edwards. Brilliant. Thanks, Pippa.
Thank you.